Hello, everyone. I'm Susan Nash. Welcome. I'm really excited about today's program that we're back to Pivoting 2021, and we have a great program tonight, an independent look at CCUS opportunities with Mike Rains and Patrick King. And we have leadership of APG with us tonight to introduce what they're doing. And then also I've invited people, and I'm encouraging people who are in the audience to join in on discussion after the presentations. We really would like this to be as interactive as possible. So I'd like to start by introducing the President-elect of the Energy Minerals Division, Mike Bingle-Davis. Welcome.
Thank you. As Susan mentioned, my name is Mike Bingle-Davis, President-elect for the Energy Minerals Division of AAPG. I'll keep my introduction short, that way I don't intrude on anyone else's time. But I would recommend anyone that's in attendance that's interested in anything that's discussed tonight, or when you begin to start to use your imagination in what geology and how geology can apply to the different facets of what we see in our society changing, the changes that are occurring. Energy minerals and the Energy Minerals Division is really at the forefront of most of what you're seeing and most of the changes that people are mentioning that are occurring or are planning on having occurring in the future. So take your time, look at the Energy Minerals Division. It's a great group of people, and we'd love to have you join. So take a look, and I'll be available for questions later. So it's great to see you all. Thank you.
Great, thank you. So now I'd like to turn over to Meredith Faber. She's a president or former president of the Division of Professional Affairs, DPA. So welcome, Meredith.
Thanks, Susan. It's an honor to be here. Hello, everyone. My name is Meredith Faber. I'm the past president of the Division of Professional Affairs. And I'm very interested in your topic this evening. It's unfortunate that I can't stay for the duration of the presentation, but building a sustainable network of energy sources is one of those things that's very paramount to our success as an industry. And so I think that it's probably a moral imperative to be able to keep track of where all our carbon goes and where we should put it when we're done with it. And so I think this is an excellent topic to pursue, and I thank all the speakers for lending their time to this pursuit. With respect to things going on with DPA, I'd like to draw your attention to our luncheon that we're having at Image, where Billy Williams, who is the Senior Vice President for Ethics, Diversity, and Inclusion at the American Geophysical Union, is going to be presenting a talk entitled Cultivating Bravery and Redefining Expectations and the Role for Scientific Societies in Leading Change. And we think that this is a very pertinent and topical thing that needs to be discussed more so within professional societies and within industry in general. So I'm going to drop that link to that luncheon in the chat box. And if you have any questions regarding DPA and what we do, I'm going to also put our email address. You can get in touch with me or current President Don Burdick, and we'd be happy to help you with any concerns, questions, or queries you have regarding the division. Thanks, Susan.
Oh, great. Thank you. So before we move to Julian Shen, who represents the Sustainability Committee, I would like to thank our sponsors, Aramco Services. So a great thank you for their sponsorship of the entire series, and also IHS Markit and Energy Freelance. They've sponsored this as well. So thank you to our sponsors. And so now I'd like to share the platform with Julian Shen with the Sustainability Committee.
Hi, everyone. Thanks again for inviting me, Susan. It's a pleasure and honor to be here. And then good afternoon and good evening to those around the world. I'm Julian Shen. I'm on the AAPG Sustainable Development Committee. And the goal of our committee is to really propagate the broad, positive, technical, social, and environmental benefits of the petroleum industry. And we're also bridging the gap between new and rising trends in the energy sector with geoscientists. SCG has recently compiled a sustainability atlas for the geosciences, And AAPG has also been working very hard on doing that, and we've just published it recently. More than happy to share that with you all. And it's really exposing geoscientists to what opportunities are out there. At the end of the day, the rocks are still the rocks. The fluids may differ slightly differently. And so that's what the Sustainable Development Committee does. To keep it brief, we have an exciting panel that's coming up at Image. I will be there in person, masked up and ready to talk with everyone. And it'll be about the new and rising future from petroleum industry to energy industry, global perspectives from a young professional's perspective. So we'll be discussing that on the panel and what that means for young geoscientists that are graduating and how to navigate that future. So thanks again, Susan. Really happy to be here, and I'm very excited for the discussions today.
Oh, great. Well, thank you. And I see that Ursula Hummus is here too, if she'd like to speak really briefly about her panel that she has at Image. Or if I got Ursula, I think maybe Ursula, I caught her off guard. At any rate, we'll invite her to speak whenever she'd like to. In the meantime, I would like to invite Mike Rains and Patrick Ing.
Sorry,
Oh,
Susan,
okay,
I'm on my phone.
Well, I just thought you could maybe say a few words about one of the panels at Image that you're involved in.
Yes, I'm going to moderate a panel we are having on what's new in energy minerals for EMD, highlighting a lot of the different committees that we're working with EMD right now. The panel discussion is going to be on Monday at 1:20. We will have 4 people in person and 4 or 5 in online. Unfortunately, some of the USGS people had to cancel. But you should check in because we have several speakers speaking on critical minerals, on geothermal, engineering, hydrogen, energy economics, and what was the other one? Tidal oil and gas. Yes. So it's going to be really interesting, showcasing our committees, the hard work they're doing. Thanks so much.
Great, thank you. And then finally, I noticed that Gretchen Gillis, our president, slipped in, so she can't get away with so easily. Gretchen, would you like to say a few words?
Yeah, good evening, good afternoon, good morning, everybody. It's great to see so many people here enjoying the sharing of technical information. And for me, this is sort of a bit of community tonight as I sit home with Dave, enjoying a little bit of dinner and enriching our technical knowledge. So thank you so much for everyone who's contributing to this series. And it's just so nice to see everybody. We'll be at Image in Denver and look forward to seeing you. And as Meredith has said about DPA, if you have feedback about AAPG, you know where to find me. Thanks, Susan.
Oh, thank you. So great. Well, I'm really happy to introduce Mike Rains and Patrick Ing, who are here to start our program on an independent look at CCUS opportunities. So Mike, I'd like to invite you to share your screen. Or if Patrick is starting, just either one. Great.
And unmute too, I suppose, would help.
Yes.
And hi, Wendy, I saw that note. I used to work with Wendy on lease line production work long time ago. I'm much older than she is, though. Well, today we want to talk about CCUS. So I think most of this group probably knows what we're talking about here, but I'm gonna try to define everything that I talk about just in case someone in the audience doesn't have a familiarity with that. So CCUS is carbon capture, use, and storage, also commonly known as enhanced oil recovery, or EOR. So we're gonna see what the new changes in the tax laws and all the hubbub about CO2 can do to help smaller operators possibly get into this space, help use some of that CO2 and take advantage of our current situation to get a bunch of CO2 out of the system and into use. So my co-author, as Susan mentioned, is Patrick Ng, Real Core Image. My company is Mars Exploration. And here's our websites down here and Patrick's LinkedIn address in case anybody wants to contact him. And really what this is going to be about today is thinking out of the box and considering what we might be able to do, and then looking at ways to interconnect things. But as part of that, with the CCUS, I'm going to delve into quite a bit of what to expect when you have a CO2 project. And let's see if I can get a slide to advance. Here we go. Okay, so as everybody probably already knows, this is a collaborative effort between the Carbon Capture, Use and Storage Technical Interest Group and the Deep Learning Machine Learning Technical Interest Group. So I'm the co-chair of the CCUS TIG, and Patrick is the chair of the Deep Learning Machine Learning Technical Interest Group. So we got to talking, thanks to Susan, and this little PowerPoint that we put together in this little demo at the end is the current collaboration results to this point so far. Okay, so our outline is going to be talking about energy transition, and I put in motion because we've actually always had an energy transition going on. It's just that sometimes the transition is long and slow, and sometimes it's changing a lot more quickly. So for us in particular, we think about Drake as the first person in the big energy transition that moved us away from well blubber to petroleum products. So we're going to talk about how to get to the flare gas as a source of CO2. What can we do with it? Then talk about some of the things that you need to consider if you're serious about looking into this. And then we'll go into a live demo from the data analytics section and talk a little bit about what some of these things could mean and try to kickstart the thinking out of the box and then wrap it all up. So when I first got to start looking at this, again, it was partly from Susan's spurring and then working with Patrick on a couple of other questions. And what we've really come up with for this is let's look at these things as a idea starter, a kickoff, a food for thought to see about what we might be able to do and think beyond the box, integrate things, looking into the energy transition as also using and integrating all parts of our energy properties and not having some things go to waste, which could be merged with something else. And I'll give you some more hints about things that we're talking about for that toward the end. So this is the view from not too far from my house. Each of these bright spots in the sky here are flares that you can see from just outside of town in Midland. So none of these are city lights. These are all flares, and this is about half of the sky. So this is pretty typical on a night, on any night really. And it just makes you wonder, what could we be doing with all that potential that's being wasted right now? So that kind of kicked off the very ideas that Patrick and I started talking about. So where can you get an idea about flared gas? Well, one of the places that you can look is the Texas Railroad Commission. They have monthly reports that look like these things where they talk about acid gas and CO2 and vented or flared gas. But these things are individual months. They're aggregated for the entire state of Texas. It's not a very granular system, and it's very difficult to work with. So is there some way that we can get this data in a better format and start working with this on a more granular scale. If I have a project somewhere, can I find a way to see what's around me and use that data to come up with an idea for something else? So this looks like a starry night picture from somewhere, but this is actually the reverse. It's looking down from the stars toward the planet. This is the Midland County border, Ector County border. These dots that you see are flares from a nighttime satellite photo. You notice right away that you have some big flares and some little flares and some tiny flares. So this is like a good place to start thinking about the spatial locations of where these things are relative to some property that you might be able to integrate with or work with. So this is from the same source. This is Anderson Geo Consulting here in Midland. And this is looking at flares that have been active for more than 2 weeks, just to show you that you can get more granular with this detail. Again, it's all based on satellite data. And you can even take it down to the level where you can identify spots where flares are actually coming from by combining these locations with high resolution photography. So Colorado School of Mines has been working on CO2 problems for a while now, and this is something along those similar lines that they've come up with. They have a satellite that they've got access to that is scanning different frequencies and identifying CO2 as part of flare gas streams. And that's what all of these dots are. This is the Gulf Coast of Texas right here to give you a scale. There's Houston, Dallas, Permian Basin, Gulf Coast. So each of these points is something that they have been able to scan with their satellite data and calibrate and estimate a volume of CO2 from. So this is the base data source that we're going to be talking about with our data analytics tool, which Patrick will guide us through a little bit more later. So let's talk about some of the things that you have to think about for CO2 itself. So CO2 is a non-ideal gas, and we'll talk about what that means more, but it doesn't behave like methane does. It's not in a linear fashion. And most importantly for us, in a typical reservoir situation, it's right on the line between a gas phase and liquid phase. And these types of reservoirs here would be applicable to carbon capture use and storage, or saline storage in brine aquifers. So the phase of the CO2 is going to play an important part in how we handle things and what you need to be prepared for when you are planning for using CO2. Okay, so there are a couple of different scenarios that CO2 can interact with fluids in the reservoir. And one of those is called miscible. We'll start at the bottom because that's easy. It's a mixing fluid. So a miscible fluid, you have CO2, gas, and water. They all exist simultaneously in a single phase. That's miscibility, or a miscible fluid, or mixing fluids. The other end of that is a non-miscible or immiscible fluid, where you have maybe a gas, or it could also be a liquid though, and may not be miscible with your oil. The chart that we're looking at right here is a percent recovery of HCPV as hydrocarbon pore volumes, and then a changing of pressure. You can see that the recoveries are low when you're in this range here. And as you get a higher and higher pressure, eventually you break over and your increase becomes flat. So this turning point here is the minimum miscibility pressure. The significance of miscible versus immiscible is how the CO2 interacts with the oil that's in the system. In a immiscible system, you do get some increased mobility, but compared to the miscible system, that is not very efficient, not very effective, and you get a lot better situation for flooding when you're at or above that minimum miscibility pressure. But of course, every time you increase pressure a notch, that takes more energy at the surface and more energy in the reservoir. So you're not really getting much bang for your buck after you get past that minimum miscibility pressure point a little bit. So let's take a look at how complex CO2 is. This is a non-ideal gas. So let's just take an example here. Well, first let's look at the scales that we're looking at. So pressure is on the y-axis, and enthalpy down here. Temperatures are the blue lines, and density are the green lines. So for example, if we take 160 degrees Fahrenheit and we follow it down to 1000 PSI, around the corner here, we get what our density value is by following this line. So you can see it's a very complex system. So the things that influence it, of course, are reservoir temperature, reservoir pressure. And what I mean by differentials is the difference between your injector's pressure and your producer's pressure, and all the points in between in the reservoir. And also, to make things more fun, the composition of oil impacts what your minimum miscibility pressure is. So if you have a 38-degree API gravity oil and I have a 38-degree API gravity oil, that does not mean that our minimum miscibility pressures will be the same. And the only way to find out exactly what that minimum miscibility pressure is to do lab testing and determine it experimentally with the exact fluid from your formation reconstituted with the gas from your formation. So another thing that makes CO2 even more fun is that with time, you increase the gas in your reservoir relative to the oil compositions. And as increasing methane starts up in the history, then your minimum miscibility pressure goes up with it. So these are all challenges with the physical aspects of CO2 that make it a little bit hard to deal with. Now, what does that look like in a practical way? Let me show you to this map view. What we're looking at here is a quarter pattern. So we have an injector in the corner and a producer in the other corner. So this is 1/4 of the entire pattern. So as you start injecting CO2, you initially get radial flow. And then as you get further and further from the wellbore, the fluids start seeing the differences in permeability, and they finger and make different tracks with different densities. And in this case, what we're showing is one track that makes it all the way over to the producer. This is what we call a breakthrough situation. This is a fingering of the gas that bypasses all the rest of the zones and all the rest of the bank here. It has a couple of problems that make this hard to deal with. Once this sees a higher relative perm interval, it quickly takes the gas this way along that pathway. And as the gas gets further and further from the producing source, what we're showing in this example is the pressure decreases. At some point, you become non-miscible and maybe even non-supercritical, and the gas will suddenly be much more mobile. And once you have breakthrough into the well at the producing leg, all of the oil bank that you've built up on the sides is abandoned. All the CO2 support that you had drops off, and all the CO2 rushes through here. From an operational standpoint, that seems great at first because you get a lot of really good response really quick. But the downside is that you quickly sweep all the oil that's in that interval out, and you're not contacting any of the oil out to the sides or recovering any of the oil that you had mobilized earlier. So breakthrough is a major concern in your CCUS or EOR type operations. Now, the same sort of thing can happen in a vertical sense as well. So what I'm showing here is an actual well log from a real CO2 flood, and the porosity zones are here, 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 and so on. So in blue, you have something that might be either a theoretical expected contribution from each zone, or this might even be an actual water flood response for what percent of your fluid is going in each zone. When you get to the CO2, you might have a situation like this instead, where you get a significant volume going in a single small zone, and between that and a couple other zones, you take up all of your CO2 and abandon all the other zones that you thought you were going to be supporting. And in the case of an EOR application, you may also have a permeability streak that's below your oil water contact. So containing where your CO2 is going, both vertically and laterally, is a significant part of monitoring and managing CO2 floods. And that'll be the same thing for a CCUS opportunity, because you are going to be taking this CO2 out and recycling it again a few times in most scenarios. So there are a few things that you can do to mitigate these things. One of the most common and easy things to do is to inject water with your CO2. A lot of operators these days use something called a WAG, or water alternating with gas process. That is, you put in a certain amount of CO2 and then you follow it with a certain amount of water, and you change the relative amounts of those depending on where you are in your flooding system. So the water creates a block which keeps the CO2 in the next phase from rushing right through these same intervals or same pathways, and helps distribute your CO2 better. Another thing that you want to be sure to do is to avoid losing CO2 out around the edges. So a containment field of some sort is necessary. What we typically have done in the industry is put a line of water injector wells around the outside of the project. It's called a water curtain. It has two advantages. It increases the pressure outside of the project, so it reduces the incentive and the relative perms for things to want to move out of the pattern. And then you have the physical water block in addition to that. So containing this as breakout or breakthrough zones, and containing it to maintain its location inside your desired area, are a couple of key things that you want to try to plan for. And then, of course, this is really more for a standard EOR, not so much for CCUS, where the ultimate plan is to leave the CO2 in the ground. But targeting the richer zones gets you an improved recovery faster and helps your economics. Okay, so this is the example of a miscible flood look, if you will. And we're talking about a potential reward of 10 to 15% of the original oil in place after primary production is complete and after water flood is complete. But that is got some caveats with it. You have to maintain your pressure above bubble point, above supercritical for CO2, and above your minimum miscibility pressure. You need to be able to get at least 5% of a pore volume per year of injectivity. So pore volume, just the pore space in the pattern that you're contacting. And what I mean by injectivity is total amount of fluid in reservoir barrels. And you also need to keep your total recovery efficiency at least 90%. That means you don't lose CO2 out of your zone. You don't lose it off to the sides. You don't have it adhering to the rock or interacting and crystallizing along the way. So if you can get all these things lined up correctly, then you could estimate somewhere between 10 and 15% of your original oil in place as your potential reward for doing all this effort on the CO2 flood. Now, even though I showed you on that miscible versus immiscible plot that CO2 is much better as a miscible project, there are times when that is not correct. This is a cartoon example, obviously, of a real life situation where you have a pinnacle reef encased in shale. What has happened with that is that it's produced originally starting in the 50s, and now it's at a very low pressure, and it has a lot of residual oil, but no real oil legs. So you inject CO2 at this case in a non-miscible fashion. It's very low pressure. It forms a gas cap and starts moving down. And as it moves down, it liberates some oil and allows that oil to migrate with depth to a lower interval. You've got a supporting water coming in from the bottom too, or perhaps you're injecting water. In the case of this real life example, that's a natural water flood, but it's low pressure still. So that allows you to condense the oil into a single smaller interval, and then you target this interval, and your target moves down as your oil moves down. So even though non-miscible flooding is generally not the best approach, there are times where it can be very good. And in this particular example, the ultimate recovery from primary, secondary, and tertiary is expected to be towards 80% of the original oil in place. So this is a rare situation, but I just wanted to show you this to note that it is possible to have a special condition, and you need to think about what your situation might be and which ones would be appropriate, or maybe even what you can get by with, even if it's not optimal. So some of the other considerations that we need to think about and plan for are well integrity issues and surface metallurgy considerations. Why? Because CO2 creates carbonic acid, and that's very hard on your equipment. So casings, liners, tubings are all things that are susceptible in the wellbore. And when you get it to the surface, you're piping it from the wellheads to your facilities. It's contacting materials in the facilities and transferring in between. So these things where CO2 is going to be in direct connection with your metal equipment need to be protected. So some of the things that you can do are nickel plating in critical areas. What a lot of operators have done is have regular tubing down to, or regular casing that is, down to the point where you're going to set your packer, and then have either a nickel plated or a chromium plated tubing or casing rather from that point down. So you don't run 10,000 feet of it, but you run a few hundred feet of it and protect those intervals that need to be protected the most. Another thing that you can do at the surface to avoid the need for special fancy metallurgy is to use dehydration techniques to make sure that the CO2 does not have any water in it. No water in the CO2 means no carbonic acid. And in those cases, bare steel and CO2 are fine together. It's the water combined with the CO2 that makes the trouble. Okay, so you need to keep in mind that you might have to replace some equipment in some places, and you want to also ensure that you have good cement behind casing. You're also going to need, if you're in a CCUS situation, to make sure that you have a way to tell what's going on with your fluids, your CO2 specifically. So some of the monitoring options that we have currently are wireline logging tools, production logs, injection logs, and neutron porosity tools run in a repeat manner. So CO2 gas is similar to hydrocarbon gas in that the neutron count rates and the porosity derived from them will be changed when CO2 is in the system. So you won't see it'll appear as if the porosity is decreasing with time. And that's really telling you that your zone is increasing in gas content, and in this case, CO2 content. Of course, the limitation of the monitoring tools from wireline standpoint is the depth of investigation. They are looking very near the wellbore. So if you want a 3-month warning before CO2 reaches your producer, this is limited help unless you have an additional well that is along the pathway and that is only used for monitoring. So something that's very interesting from the geophysics aspect is 4D or time-lapse surveys. So there's different kinds. Crosswell is running into one well with a geophone or hydrophone assembly, running into another well with a source, and you image between those wells. And what you see in the 4D time-lapse space is changes associated with the change in density, and the change in density is associated with which fluids are in the porosity. So you get a snapshot or 2D image of what's going on in 4D space. This little cartoon down here is an example of a crosswell seismic survey. This is a real life example, but obviously with the cartoon categories on velocity change. And what we noticed in this one is that we were injecting CO2 above the oil water contact and expecting all of our CO2 to stay in this interval. What actually happened is that we got the anomaly underneath the oil water contact. And in this case, that's a free oil water contact. So that's the start of the transition zone. And we deepened one of the wells to capture whatever that fluid was that was causing that anomaly. And it was the CO2 and the oil bank responding to that CO2. And for a couple of weeks, I think we had the largest oil producer in New Mexico with that central well there. So this stuff does work, Crosswell does work, but its limitation is that it's a 2D snapshot and you have to go back in and reacquire it every time. In a similar fashion, you can do Crosswell electromagnetic surveys, which look at the electrical change over time between wells. And you can interpret in a similar manner what's going on in between those wells. Vertical seismic profiles give you a little bit more of a 3D view close to the well, but at least it is 3D. And then of course there's surface seismic data, which is fully 3D, and you can repeat that. But again, the constraints on those are they're expensive, time consuming. You have to take wells down and bring them back up, and you don't get a real-time answer. There are some other developing tools, some of which seem to have some good potential. Induced surface electromagnetic imaging reduces your need to have to go into the well to get the electrical imaging, but then you have to worry about the depth and the resolution with this approach. But I think this has a lot of potential in the future. Natural source electromagnetics, that's a lightning strikes, where the lightning is used to induce the electrical image in the reservoir. And of course, the depths are limited. CO2, if you're gonna look at EUR if you're gonna look at CCUS, you're limited to depths approximately 3,000 feet or more. So that leaves a small window for this. It does still have a coarse lateral resolution. And of course, you're dependent on lightning striking and it being at a convenient time for you to get the image. Something that I've seen a little bit of, but need to investigate more, is crockless waves, which are a signal that's easy to transmit between wells, and it's traveling along the hydraulic connectivity. So the advantage there is that if those things are hydrologically connected between your producer and your injector, that's probably going to be the path where your CO2 is going to. And it is cheap and easy to do, but I think it still needs some work on the fact that it's a 2D profile. You have to estimate some things, and it's still a newer technology. Like to see some more work done on that before I would use it myself, but I think it has a lot of potential. So at any rate, all of these things lead to the fact that you're going to have some geophysics built in. It's going to be an integral part of CCUS, and knowing where your CO2 is going at any one time, making sure it's staying where you want it to be. And of course, that is a key to the security of the CO2, which your tax incentives are going to be based on if you're doing a CCUS project or a CCS project. So to start off, if you think you might have something that you want to look at, the first thing you need to look at or start thinking about is a reservoir characterization. How much oil are you going to be able to get out, and or how much storage potential do you have in your reservoir? How are you going to contain the CO2 and make sure that it doesn't leak off laterally or vertically? And what about the rates? How much are you going to be able to put in at what rate? And these days with induced seismic activity, we all want to worry about also what's an appropriate rate to not cause some other problems along the way. And with your source of CO2, are you going to use this flare gas that we've talked about? Is that going to be your primary source, or is that going to be supplemental to something else? Are you going to try to tie in with other industrial processes? Ethanol plants are the most common anthropogenic CO2 projects that have been started to date, as far as I'm aware. There are other things that produce electricity or produce CO2 though, and some of those might be appropriate in any one particular area. And then of course, the stability of the source. If you're doing this as a CCUS project, your EOR system needs to have a stable source of CO2. Flipping it on and off and high and low is going to create problems for your workflow instead of making things easier. So if you can work through some of these issues and get a source of CO2 that you're happy with, you're far down the path to getting something that might be easily workable. Okay, so some of the things that go into the economics that you need to think about then, it's of course distance to the source. And if it's a scattered source, like if you're talking about pulling in flare gas from 50 flares, it's also the amount of pipeline, not necessarily the distance on the map, but the amount of pipe that you have to put in the ground. Or are you going to try to do some other transport? You're going to truck it, bring it by rail. How are you going to get it from point where it is to where you want it to be? And then again, stability of the sources. What are you going to get for the tax incentives? It is my understanding that the new CCUS and CCS prices that were proposed have not gotten very far in the Senate and House, and that we're going to be, at least for now, stuck with $35 a ton for EOR applications or CCUS applications, and $50 a ton for saline aquifer or CCS applications, which works out to be about $2 an MCF for EOR, or closer to $3 for brine storage. They did, however, keep so far the direct pay options. So that eliminates the need for these massive and complex tax partnerships where the party generating the CO2 and the party handling the CO2 and the party storing the CO2 might all be different. So along with those tax incentives, what kind of structure are you going to have for your cost sharing? Because the most expensive part of the CO2 acquisition is compressing that CO2 after you've got it separated. So it's an atmospheric pressure. You can't use that in any pipeline, and you can't really use it in a reservoir either. So a lot of electricity has to go into bringing that up to a supercritical phase. And then we've mentioned this monitoring program a couple of times, but I want to tag this one more time. Knowing where your CO2 is at any one point is going to be critical to making the regulators comfortable that you're meeting your obligations to capture that CO2, maintain that CO2, and not lose that CO2 either laterally, vertically, or some other system that you've felt at, like at the surface or through well bore problems, whatever it might be. So keep in mind your workovers, and you can get somebody to help you walk through all the steps. Have some people that I've worked with before later on in the slide show as references, and you can start with them. I'm not necessarily saying that everyone on my list is the number one person, but I've worked with each of them, and it's a good place to start. So how much oil are you going to get back, and then how long it's going to take to get that, and when are you going to have to employ your capital to do so? So that leads us to, how can you evaluate all these potential sources, and what are you going to do to get to some answer that might help you? Well, in the past, it's been a very long, involved, drug out process. My just explaining it was a long, drug out process, and this has been even worse. So now, though, we have some data analytics tools that Patrick's going to show us here in just a second. And we think that these tools are going to help make at least part of this decision making easier and bring together maybe some target areas, because it is all located in physical space and can be organized by its location there. So at this point, I think I want to switch over to Patrick, and he's going to drive. This is the live demo. So Patrick's picked a spot just outside the city limits of Midland, actually still inside the city limits of Midland. And what we see here is a bunch of data points. These data points are individual flares. Patrick, are you unmuted? Can you talk as you desire?
Hey, I'm good. Keep going,
Okay.
Mike.
Okay, so this is a 3.5 or 3.1 mile radius, 5 kilometer radius that clicks up in a spot. You want to just pick a new spot, just show them how it works?
So this is near Sprayburn.
Okay, and you can see all the flares there. If we scroll down a little bit, the first thing that we're going to see is the lat long in the center of that thing, and then the next thing is a list of what we're looking at. And I think that they won't be able to see my mouse, Patrick, so I'm going to rely on you to use your mouse. So in this case, there's 211 observed flares in that 3 mile area outside of Sprayberry. And then Pat's got some statistics listed through here for each of those things. And again, that Colorado School of Mines project, the flaring monitoring website that we looked at, that's the source for where all this data is coming from. Oh, he's got it right there.
Yep. So this is Permian and this is Eagle Ford area. And
a
we're in
couple in the
Permian.
Dallas-Fort Worth. So in this example, we have the individual flare and the area aggregates of P50, P90, P10, Swanson's mean, and average, so that you can get a feel for how much variability are in the CO2 volumes that are coming out of the flares in this area.
And these would be in unit of 1,000 cubic feet per month.
Are my favorite units.
And down here is the like a histogram or distribution of those same information.
So you can see that most of the events were less than 20,000 cubic feet. And then you have a few scattered that are higher, but they're single items. So that one, for example, that Patrick's hovering over right now is a one event. And the way this data is organized, it's combined into month events. So one event for 1 month gets one estimate of volume. at one location. So now we've got the operators that are in that circle and their minimum, maximums, and averages, and how many flaring events were recorded for them. Oh, and by the way, this data goes back to 2019 when the satellite was launched. So that is the starting point. No data before 2019. And now here you can see the number by operator, the number of events, that is. And then here's the nitty-gritty detail. So in this system, cluster ID is a local, not an absolute ID. So as you move the circle around, don't rely on that 1219 being the same cluster everywhere. That is not like an API number. That's just a local ID for the database itself. So each of these can be sorted, so we can sort by operator and get all of the Apache together and Crown Quest and Pioneer together. We can sort it by cluster ID, size, date, volume is my favorite, and get it from small to large and get an idea on what you're looking at as far as how many MCF per month each of these flares is doing. And those are all associated with a specific date. So you can see that, so just pick one, Patrick. Well, so that one is associated with that 2019 date as when it made that 21. So that's not the same cluster giving you the statistics through time. It's just the individual points. Anything else about this section?
Well, I guess the one that is a quick complement to the flaring monitor that you get from the monitoring site is that it's just like instantaneous look. It's just for that month. So here we demonstrate maybe just having the statistic. This is like a cumulative view. So the thickness of the thread, well, each one of these is proportional to the amount of flare for that month. But the total thickness under here attribute to a particular operator. It's just a quick look like the cum production. So here within the 5 kilometer radius, these are the distribution for that period for the 26 weeks under the observed data. So again, it's just a quick summary, but at least you get a sense of the key thing is within a click, you get a feel for what the distribution is, but more importantly, get the 3 Ps up in front. So you can start thinking about, get a feeling for the kind of variation so that you don't go down too far before you realize, hey, using the average might not give me the whole picture. So Mike, you want to take a look at a different location?
Sure, you want to go over by the airport?
Okay. Well, I'm just going right by the airport.
Yeah. I mean, the Midland International Air and Spaceport, excuse me.
Yes, that's the future of E-plane, E-jets.
Yes. And we actually do have a space company that has a hangar out there, X-Core.
All right, so here, maybe I just quick, this is actually Google Maps, some of you recognize. So if you take this little guy and you move it over there, you can actually go and see if there's anything available. Yeah, interesting to look at. So you can actually see if you're going to do any CCUS. Now there's a rig over here, and project. You want to kind of get a quick look for a feel for the environment. And that's right here. So that saves you driving out there if you're far away, and that's make it a little bit greener. So again, this has a very different distribution. Now, you can actually see the individual flare volume. So I understand if you have certain threshold, you say, hey, I need 20,000 or whatever. as a starting point, and you can sort of screen those as well. Again, this gives you a little feel for different players in the area. And again, if I go back down there, it's a quick look. For this particular area over a particular period, based on the observed in estimated from infrared satellite data, that is the cumulative flaring attributed to the one operator, and so what's the other. Mike, you want to add anything else?
No, I think that's good. Just the individual threads there show up and the operators show up. So it's just a nice quick look.
Yep. So now that's flaring. But what Mike talks about is, hey, we do want to get down to see what happens in addition to flare gas. Now, this is where the magic, I'll explain it later. But could you mention, this tells you something about where those flare gas might come from.
Yeah, so this is the area geology, and this is actually pulled off the horizontal wells. It's not the exact same wells in that area, but it is the exact same circle location. So you can see that there are quite a few reported Wolfcamp, a few Strawn, Sprayberry, a couple Pennsylvanian, some others, and so on and so forth. So this can be pretty helpful for you if you can get an area where you think the flare volume is of interest for you and you want to cross-check. You can see what these formations are that are common in that area and maybe get a feel for, I know that Sprayberry has X% CO2, so I have a high confidence in that CO2 volume that's been estimated, or I have a low confidence in it and I want to look somewhere else.
And in fact, these are information gleaned from the Texas Railroad Commission. Now, there's one more thing. Since we're talking about expanding the way of thinking energy, flare gas is one. Maybe repurposed shale wells would be another, but there's a whole area of exploring geothermal potential in sedimentary basins. So this is also data coming from a different source. This is coming from the SMU Geothermal Lab. It just happened, if there happen to be measurements within that 5-kilometer area, it will show where the samples, the depth and the temperature. And in addition, for those who are interested in data analytics, it also gives you a first linear fit, like a simple proxy model, what the temperature gradient might be. Now, of course, then it gives you some idea that, hey, maybe I should pursue a little bit more work and refine and figure out how deep these wells. So now we go to the next, maybe a picture of understanding the depth with certain temperature in mind. Well, how many of these wells are at that depth? So again, this go back to using the same information that above from the formation. Now this shows the distribution of the total vertical depth of those wells.
Yeah, so in this case, like we have a large number of wells between 9,000 and 10,000 feet in those two bars there. We can go back up to that geothermal gradient estimate and see what temperature would we expect down there.
Well, if it's about 10,000 feet, it's about 150 Fahrenheit.
Yeah. So now you have an idea of if that's something that's of interest to you or not, and if you can do something else with that. So, and we'll talk about some of the things you can do that at the end.
So that is really the key of when we pull these three things together: the flare gas from eye in the sky, the shale well production data from the Texas Railroad Commission or other agencies, and then the geothermal information that cleaned from SMU's geothermal database. So within that one geographic location, within the radius, then we can bring it together and start thinking about what we can do. Thank you, Mike.
Yeah, thank you.
Great. Well, so gremlins have attacked my computer. So Zoom is frozen up. So I can't really do anything. I was fortunate to be able to log in using a different computer, but there's not that much I can do. So, but anyway, I'd like to invite people to, let's look at the chat to see if there's any comments or I'd like to see if David Merchant has made some interesting comments. David, would you like to open up your microphone and describe what you're talking about?
Yes, I guess this goes back to Michael's regards too, is that when we talk about conventional oil recovery in the Permian Basin, we've been doing this for 49 years and been doing it really effectively. But to me, the real key in the future is when you really want to eliminate the flare is targeting unconventional. And I say that because if you do huff and puff, you can get 2x or 3x primary oil recovery. And I wrote a paper specifically to address this. If anybody sends me an email, or I'd be more than happy to send you that along with 5 or 6 papers that I have on conventionals. But going back to unconventional, I wrote this paper specifically to address Permian Basin. So if you take 1,000 pad area, about a 40 by 50 square mile area, and you sequester CO2 into it, you can sequester about 4.5 trillion cubic feet of gas, with conventional or with huff and puff. Nobody really talks about this, but to me, the solution in the Permian Basin goes along the same thing along the Gulf Coast, but the Permian Basin specifically is I was out there for the CO2 conference 2 years ago, and I do remember the smell that came out of Midland, and also being able to see the flare. So, my goal specifically is that, if you really want to put out the flare, then what you need to do, is if you really want to put out the flare, is let's do it the best way and direct it toward unconventionals. And let me put my view back up, I guess. It's not working. But anyway, that's what I wanted to do, is focus on.
Oh, that's good. Yeah, and I would make you co-host, but since my host computer froze, I can't do anything. But I really like what you're saying, and it's nice that you put some things in the chat. So anyway.
I'm also an engineer, so maybe I'm on the other side, but
That's
I've learned a
great.
lot over the last 45 years of doing this, and specifically for the last 35 years in the Permian Basin. In the mid 80s, they took away my 2,000 barrel a day wells or 10,000 barrel a day wells when I worked Africa Middle East region in '86. Shipped me upstairs with Amoco upstairs about 6 floors to work the Permian Basin. And at that time, tertiary oil recovery was 6 to 10%. And we didn't know what we were doing, and then it was my responsibility to do modeling. And our little group came up with tapered WAG, which extended out to 18. And then when you look at today, we're up to, we get up to 26% or more. And so, the strides that we've made over the last 49 years, is really tremendous. And the Permian Basin is the key area, but it's also the major target area in regards to when you look at flare. So the question really ought to be is, how can I put out the flare? How can I do it economically? And and to me, since I'm a reservoir engineer, my whole the goal specifically is let's get this thing moving. And but there's a lot of issues from the conventional EOR world. The 45Q is fine. But when you're really looking at it, is now I've got federal government looking over my shoulder and monitoring every CO2 thing that's going into it and out of it. So to me, until you get poor volume rights by state, which Texas is headed toward that direction, and actually get control in it, then you get the government out of it, and you get politics out of it, and you can actually make something happen. So And I'm rattling on too long, but I'm also focused along Houston Gulf Coast from a CCUS hub standpoint. Is how do you put the flare out in the Permian here? And with the main target really being, because of issues of pore volume space, is that it's not going to be Denbury or Hillcorp or any of the other, the EOR portion of it, but let's go offshore in deep sailing and eliminate, and which Thales and Exxon, other companies are headed that way too. So it's a crazy world. We move from one day to the next, and who knows what's going to happen tomorrow. But I look at the CO2 world or the sequestration world. I've been in it for 21 years. Depending upon who's in president, depends upon what goes up, what goes down, and we haven't made any progress at all.
Well, let's, really good points. And I noticed that Ursula Hummus has a question, and Mike Raines asked if she could expand it. So Ursula, are you there? Would you like to?
Yes, I am here, and I don't know, I'm sorry, I'm on my iPhone and it's just really weird. So I cannot see my face. So I was just curious about, because most of the charge of CCUS is to sequester it permanently and not just to use it for EOR. And so I was going to ask Mike, because I know that he worked for Kinder Morgan and we've met and everything during one of those SACROC projects on carbonate EORs. That do you also use CO2 just to sequester or only for EOR?
The idea would be in the CCUS that eventually you would leave it in the ground. So its primary purpose is EOR, and then your secondary purpose is instead of pulling it back out and taking it to the next project or selling it to someone else, you leave it in the ground.
Yeah, I think that's a fantastic use of the CO2. I mean, that would be fantastic. And is it working already?
CO2 as EOR, you mean, or?
Well, I know a CO2 as EOR is working, but to leave it in the ground, I mean,
I don't know of anybody leaving it in the ground right now. Still the active projects, as far as I know, the ultimate idea is to leave it in the ground, but you keep recycling it until you get to that break-even point where you can't make money anymore with your credits or with your EOR. And instead of then pulling it off, that'd be the time that you start plugging wells and leaving that CO2 resource as a in the ground stable thing, as opposed to keeping it moving anymore after that. Dave,
Okay.
do you know of anybody who's shut in projects at this point and left it in the ground?
There has been a project in the Permian Basin where, injected into the gas cap and created and went down. And then they thought they could deplete it back up and put it back in a line and resell it again. Well, most of that's still trapped. And I forgot what the field is now, but
I think that's Wellman unit, I think.
Yeah, and then they went back and you put CO2 back in the ground, and now you're generating oil again. And even though it's kind of like a huff and puff on a reservoir basis, and you get more oil out that way too. But to answer her question, I guess really and truly, when you look at CO2 trapping mechanism and phase behavior, that's the main driver in regards to trapping CO2 in the ground. And beyond that, to me, that's the main driver.
That's great. Well, we envisioned this as a somewhat shorter and more like an APG Academy, a hybrid, rather than having lots and lots of speakers. So we can go more in depth because so many people really want to know how exactly to do it, how to get into CCUS. So, this has been really wonderful. So Gretchen asked a question. Gretchen, would you like to unmute and ask it? anyways,
Sure. So Dave and I are sitting here kind of talking about this, and our question is, when you're conducting an EOR project, how much CO2 is typically produced?
You are recycling the CO2, so it's kind of a unfair question, I guess, because you're buying new CO2, putting it in the ground, then you've got some CO2 that's in the system in the reservoir, and then you've got some CO2 that's coming out, you're recycling it and putting it back in. So which part do you count?
Yeah.
But the idea is that the idea is that you keep recycling as much CO2 as possible, right?
Yes, right.
But in
the
practice,
upper 90s.
how close to 100% efficiency do you achieve?
It's 95%, but is the accepted number that kind of across the board, because you're always going to have some flare associated, some, over 20, 30 year projects, from that standpoint. So it could be 95, it could be 98%. I mean, it's a high number, and because it's not going to leak out. It's all going to stay in the ground. But the accepted number is really 95. And I've been to a couple of webinars and different avenues, but that's what people more or less accept. Because what you're doing is you're recycling CO2 in order to make more oil. That's the whole purpose. That's what gets you beyond 8 to 12% recovery, because you're going to end up using that same CO2 over and over and over again in order to recover. So the longer you can go, and then at the tail end, at the end, is that you can't go from class 2 to class 6 like some people think, because, well, I need to put more CO2 in. But if you got to put more CO2 in, you got to generate more oil. So it's not like a tank. It's really like it's like a conveyor belt. Probably best example.
Yeah, that is a good example.
The question in here. Yeah, this is Mary Vanderloop. And some stuff that I was listening to that Steve Melzer was talking about, he said approximately 75% of the CO2 stays in the ground, for example, in the SACROC unit. And I know the SACROC unit, they've been buying CO2, for a long time, I guess, from up in the Bravo Dome area. So if they've been continually buying CO2 and putting into SACROC, I mean, if they were just recycling the same CO2 over and over again, that would mean that none of it were staying in the ground. But if they've been continually purchasing CO2 for SACROC, a bunch of it has to be staying in the ground. And I thought I heard from Steve Melzer that something like 75% of it stays in the ground. Not positive about that.
Let me, I know Steve for forever. I actually worked SACROC for Pennzoil way back when, and then with carbon, and also did the same thing with Shell CO2 company, or when they actually came up to buy it. I got a long history with it. And the CO2 that you purchase, you inject, and then you recycle it, and you recycle it through time in order to get more oil out. And but in the end, the tail end of that is that 95% of what you purchased stays in the ground.
Way to shut it in.
95%.
And Don
okay.
had
Yeah, thank you.
Yeah, I see Don had a question in the chat. It's not usually pure CO2 that gets injected, is it? But yes, it is. The pipeline spec is it's got to be over 95% pure. So, and that's also when your miscibility starts being impacted by your CO2 fluid. So it does have to be relatively pure. I think 95% is your bottom number.
Yeah, let me add, and I apologize for this too, but let me throw this in too, in terms, because you looked at the phase diagram in regards to, yeah, I have to be 100% up here to be above minimum miscibility pressure. But when you really look at a reservoir in regards to conformance, and this is the reason why we want to tapered wag, is that if you can control the amount of fluid going through the fast zones, and even at below MMP, you can operate below MMP. In fact, the pilot out had a 14 API gravity crude out in Wilmington Field in Los Angeles, and they ran 3 pilots, and they didn't have massive CO2 breakthrough. It wasn't, like they were making 200 or 300 barrels of oil a day, and the gas wasn't streaming through. So it's not like you have to operate above MMP, it just makes it the efficiency more easier to do.
Looks
Michael,
like
let
Jeff
me,
and Ross. Oh, sorry.
oh no,
Sorry, Lynn.
okay, so that's interesting. So it's gotta have a 95% purity for the EOR projects. Is CO2 storage and disposal held to that same standard?
There's no reason for brine storage because your CO2 is not interacting with anything. It could be acid gas for all you care, as long as that gas doesn't dissolve rock or cause some other reservoir problems downhole. If it's just the counting molecules, it's just counting the molecules. And if you mix it with other pollutants, as long as they don't interfere in the reservoir space, I don't think that EPA would care.
Question.
I don't think anybody's ever asked them that, though. I haven't heard anybody ask them that.
I think we've got some questions from Lindsay, Ross, and also from Catalina and also Jeff.
I have a question, but can you hear me?
Mm-hmm.
For David. First of all, I agree 100% with him. The vast preponderance of wells are unconventionals, and just by that alone, the volume is phenomenal. But one of the complexities that occurs to me, David, first of all, go back to 1977. My first assignment at Shell was to find CO2 for the McElmo pilot project, or McElmo Dome 4, the Wasson project, which for Shell. So it's been around a long time, like you said. But what thought that occurs to me on the unconventional is we're doing 30-stage fracs. And so we're fracturing the reservoir extensively. And this could go to Michael too, is that seems to me bypass might be an even more serious problem in those reservoirs. What is you could cylindrically model, or do you look at the reservoir as a whole in a model like that with the fracture analysis?
Well, I go back to fracture volume. And a lot of this really depends upon how much CO2 that you can fill that fracture back up, and how you get it back to each one of these stages. Since you're going to do huff and puff, is how high do you want to go back to the original frac pressure? You know, how much of that pore volume can you connect with this or with the surface area with the CO2, and then be able to bring that back?
Stimulated pore volume.
A lot of that really depends upon a compositional analysis of the oil and the CO2, and whether or not to me, I can inject, it's a compositional world, whether it's CO2 or whether it's methane or propane or butane, it doesn't make any difference. But going back to the question in regards to unconventional, is I look at each area, as long as I don't have any daughters and things running off to talk to other people.
Yes.
I look at each area as a single model. And then it gets back into how do I model that in regards to how much do I put into it? How much can I get it out? How many cycles can I do it?
A cylindrical wellbore model for a horizontal?
Well, it doesn't.
I think it has to be for the whole.
It really doesn't make any difference. I mean, well, let me say it has to model to me, and I live in a compositional world. So yeah, I would like to be able to compositionally look at all the different interfaces and what I connect and what I don't connect with.
Mm-hmm. Certainly, we see enough parent-daughter well interference and drilling blocks, zipper fracs at the same time, that I think you're going to eventually have to treat them all as a unit.
Yeah, but this also gets back to what we learned in SACROC, what we learned or what I learned back in Slaughter State Unit back in 1989, is that if I can build a curtain around it, a water curtain or something like that, and contain the pressure, then I can get more oil out of it. So you got to think out of the box. What's next down the road? What kind of new technology will come along? I'm just looking at it from my perspective, is that age 72 is that, what is next? And then, but then I look at why aren't we really pursuing, if we really are diligent about putting out the flare in the Permian Basin, then yeah, we need direct air capture. We need something, or we need something, or we need net power, or we need different things in order to or to either use that gas either to inject that gas or to use that gas in order to generate CO2 in order to make more oil. You know,
So Lindsay Ross has a question. Lindsay, you want to jump in there?
Yeah, sure. Thanks. I put my question in the chat. Was just any comments, Michael, on the net CO2 balance as a function of that which is injected versus that which is produced on combustion of the enhanced oil recovery?
I can't remember what that number is. I've heard that discussed actually at the CO2 conference last year. Dave, do you remember that number? Were you there at that discussion?
I'm sorry, what was the question again?
When you consider CO2 injected and then the enhanced oil recovery oil recovered from that CO2, and then take into account combustion of CO2, what's that net balance?
Yeah, I don't know. I know Chuck Fox at one time did an evaluation on SACROC to see what the input in and output out, you know, and how green is green, and that's not my world.
Yeah, I suppose the question I'm asking is, I'm not trying to put anyone on the spot, it's just an obvious one to me at least. And the end use of the enhanced oil recovery is not the responsibility of the person that produced it by any means.
Yeah, but it's still greener than producing fresh oil and having 100% of that CO2. I just don't remember what that number is, but send me an email or something and I can track down who it was that was talking about that and get you a number. I hate to even say what I thought it was because I could be way off.
Yeah, no worries. Thanks for taking the question.
Sure. And thanks for explaining that, because I didn't quite understand where you were getting at in the text. Voice is much easier on those things.
It totally is. I think we had another. Say, Dawn, did you have a few more comments?
Oh, we have so many questions for Michael. He is just an encyclopedia of knowledge for the CO2 and CCS. Can you talk about some of the migration risk, Michael?
Sure. You want specifically to talk about
I'm just thinking about, we have like what, 10,000 orphan wells all over the Permian, right? So how difficult is it to build that water barrier in places like the Permian, where we've just got orphan wells all over the place?
Yeah, when you have a lot of old wells that you can utilize any way you want, that does make it a lot easier. If you're starting a brand new project somewhere with no infrastructure, you're going to have to think about your directional perms and where those are facing, and make sure that you establish the curtain in the best place. A curtain is just a series of water injectors. And sorry to use lingo more than necessary, but establishing those is going to be critical, and it really gives you a two-phase protection. You've got the physical water blocking that area, and then you have the increased pressure, which drives the fluids inwards toward the middle of the project instead of letting them leak out to the sides.
What I was most impressed with our conversation earlier today was that these kind of projects aren't just for the big operators. I didn't realize that until today. That Michael, you explained that these are projects almost any size operator can take advantage of.
Yeah, could anyway, and that's the hope. To think outside the box and look at what if we can combine this with something else? Maybe we can get a little electricity off the methane that we're flaring and take the CO2 and enhance our oil recovery with it. If it's a special situation, like out in front of the Horseshoe Atoll, and those not from the Permian Basin, that's a big platform that's a high carbonate development. And then out in front of it, it has a bunch of small pinnacle reefs. If you happen to own one of those pinnacle reefs and you happen to have some flares close by, and you could supplement that with cement plant CO2, or maybe get some electricity off your flare and sell that to reduce your cost. You can start combining some of these things and end up with additional oil, less pollution, and better economics. So, and that's the hope, is that we can get to that stage where we become like the general business front, where mom and pop stores are what, 80% of the total businesses in the US, the business volume in the US. What if we could get to a point where it was easy enough to do that all the small and independent operators were able to access this technology and this process? Maybe we could have the same thing here, where 80% of the CO2 stored and used is the small guys, not the Walmarts and the Targets of the world.
Hey,
Absolutely
just
love
one
that,
last
Aidan.
one last thought. I know that John Holbrook was talking about the Earth battery. Now, just think about Permian is relatively cool. You go down to Eagle Ford, the hotter rocks. So if I might just entertain that idea, I want to share the screen. And so right here, if you go down to a little bit like Kennedy, south of San Antonio, you go down, you can look at the depths and the temperature. These get up to about 350 and 400 degrees Fahrenheit. So now what Holbrook was talking about, if you can use the CO2 as a working fluid, but somehow, even if they're not quite up there, you can spike it and then use it as a working fluid, then that would be another way of creating real working Earth battery. Thank you. For energy storage using existing wells.
Oh, that's great.
You know, if I could add in one thing to that though too, is that whether it's Eagle Ford or whether or not it's whether you go up to North Dakota and things like that, it's still a compositional world. So people think about injecting CO2, but there's no reason why you can't inject. I mean, because, well, actually, depending on where you are in the Permian, it's a lot easier because of Oxy, because they rather get the CO or get the produced gas going back to the coast. But when you get down to Eagle Ford and stuff like that, it may be a lot easier injecting the wide rate or combinations of different fluids rather than just CO2, rather than flaring it. Just for perspective.
And maybe just for everybody, I sent the links. What I want to point out is that I start doing this with 3 separate apps: the flaring, the shale wells, and then the geothermal. They're separate, right? Because I was thinking people look at it differently in community. But once I hooked up with Mike, he was pushing, and then I understood, well, it created a lot more value when you bring it all together. And that's what you saw tonight. So I hope it's a starting point. And in future, we can also start thinking about other forms of energy. And so this tool allows us, think of it as a search engine, but it's just a geo search engine. Instead of Google, you type something, you get a bunch of things back. What I hope is to make this geo search, so you click on a map, because 90% of the time we start with map, exploring ideas. 90% of the time we come back to a map and pick the drilling location, commit dollars and capital resources. So that's a natural way to do it. But the key is that bring all these dimensions so we can start thinking about energy. Well, maybe energy transition has many moving parts, but the key is we can deliver, like you said, 80%, 90% reuse of something, and that would be good for everyone. And
So
the smaller players.
Yes, absolutely, Patrick and Mike. That was just so great. And I've put in the chat a link to Serathis.com, and that's a collaboration platform that APG is using, and you can join for free. And there is a collaboration space for tonight, actually for all of the pivoting. And Mike and Patrick have already put the links and information about flares in there, and then they'll put more. And there's a challenge. So anyway, we want this to be ongoing and for people to continue to learn after tonight. So anyway, well, I think we've pretty much we're out of time. This has been really great. So much interest. And Gretchen, I'd like to let you have say the final few words.
Sorry, it took me a second to unmute. Thank you so much, Mike and Patrick, for your presentation, and Susan for being a wonderful host, and for all the interesting conversation that we've had. This is the type of thing that makes me really proud to be part of AAPG. just this sort of spontaneous sharing of insights and information and challenging each other and learning. So thank you so much. And I hope to see as many of you as possible who can get to Denver. AAPG is facing some really difficult times. And one of the best ways you can support the organization is to attend Image in person. If you can't attend in person, please sign up online. But in any event, thanks again, and hope to see you again soon.
Thank you, Gretchen. And I'd like to thank everyone for attending, and also thank our leadership of Mike Bingle Davis and Meredith Faber and Julian Shen for saying a few words, and also Ursula Hummus, also leadership. And just want to thank you again, Mike and Patrick. And I'd like to let everybody know you'll be getting an email with a link to the reporting. And please go ahead and sign up for Serathis and sign up for Image. Thank you. Good night, everyone.
Thank you.
Good night. Thank you. Bye.
Bye.
Bye.